Hello, so we are continuing 10.1, Introduction to Vectors. So we did the first half in the last video. So if you didn't finish that, make sure you finish that first, and then we're going to continue with the notes today. So today we're going to look at describing the angle in both of our two forms. So because vectors have so many real-world applications, we're using physics, we often talk about the angle measures in terms of our cardinal directions. So like actually relating it north, east, south, and west. So just a reminder, your cardinal directions. North, it's going to start at the top. So this is different than where we start like 0 degrees and trig is over on the positive x-axis. But when we talk about north, north is like our 0 degrees. And then we move around east, south, west. Okay, so if I want to describe these vectors in terms of their cardinal directions, we always use two angles to do that. So we can see here we have our east label. I know that north would be vertical. It's a terrible line. And when I look at this 30-degree angle, we would describe this as 30 degrees going towards north, so we'll say north of east, right? Because it's a little bit above east. It's going closer to north, so 30 degrees north of east. Okay, the next one here, I have my north label. Looks like it's going towards west, so we would describe this as 20 degrees west of north, right? The next one here, I have my west labeling, and I can see it's a little bit below that, but when I think back to cardinal directions, it's getting closer to south, so we would say 30 degrees south of west. And then lastly, I have my east labeling. Okay, so this one, it's again getting closer to south, so 40 degrees south of east. Okay, so if we want to write an angle in terms of the cardinal directions, this would be our method of doing that. But we'll look at the same exact angles, and we're going to write them as standard position of angles on a coordinate plane. So that just means, okay, you're going back to what we know about angles like from trigonometry, where 0 starts here, moving counterclockwise, 90, 180, your 270 is down here, and we're kind of relating that back to our cardinal directions, okay? So when I look at this first angle, you have to kind of imagine this angle on your coordinate plane. So this angle is in quadrant 1, 0 degrees, right from a regular coordinate plane. So in quadrant 1, this is still just a 30-degree angle. Nothing's changed, right? I still measure starting at 0 and moving counterclockwise. Now, my next one is where things start to change a little bit, so I'm going to draw my axes. Okay. Now, north on our regular coordinate plane is actually a 90-degree angle. So I'm just drawing the axes. If I want to measure this one, moving counterclockwise, it's at 90 and it's continuing to move counterclockwise. So I like to think of this, it's like 20 degrees after 90 degrees. That word after indicates, okay, I should add. So we would call that a 110-degree angle on our regular coordinate plane. Next one here. Draw your axes in. On the regular coordinate plane, the west angle would be 180 degrees, and I'm moving after it. So I'm going to add 180 plus 30, kind of like we did in the last one, because it's continuing after 180, making this a 210-degree angle on our regular coordinate plane. And then our last one here, kind of a tricky one. Okay, so I have east as our 0-degree angle. Remember, for angle measures, we move counterclockwise when we're talking about our regular coordinate plane, not the cardinal directions. Okay, so this 40 degrees is telling you the little measure right here. Okay, but I want to know this bigger red arrow, and I can think of, well, if I continued all the way around, yes, this starts at 0, but that's also a 360-degree angle, and it looks like I'm just a little bit short of that, right? Specifically, I'm 40 degrees short of my 360 all the way around. So to figure out this red angle, I can do 360 minus 40. So in terms of our regular coordinate plane, we would call that a 320-degree angle. Okay, think of it like it's 40 degrees before 360. Okay. Now we'll look at a few actual calculations, some basic vector calculations. So it says here, for 1 hour, you travel east in your car, and you travel for 100 kilometers. Then you travel south for 200 kilometers. So let's draw that picture. So let's say you start here. You travel east, so going to the right for 100 kilometers. And then I would turn, and I traveled south for 200 kilometers. We want to calculate the magnitude and direction of your displacement. So remember, displacement is the shortest distance from the beginning to the end. So the shortest way to get from this point to this point would be a straight line. Oh, that's not straight, but you get the idea. So a straight line here creates that nice right triangle. Right, so we're just tying in those calculations we talked about in the last video. So I'll start with the magnitude. And let's give this displacement a name. Okay, let's call it a vector v. Right, so we're going to think of it like a vector now, kind of incorporating our new stuff. So this vector v is what we're looking at, the blue line here. The magnitude of that vector, I can find that. So the magnitude, remember we use those absolute value looking bars. They don't mean absolute value, they just look the same. And we can find that with our Pythagorean theorem calculation. So we'll do the square root of our horizontal distance squared, so 100 squared, plus the vertical distance squared, 200 squared. Okay. And you can just type that all into your calculator. Because these are such large numbers, we're fine actually getting a decimal here and just rounding. Type that in your calculator, and I got 223.6 kilometers. So that would be the shortest distance between those points. And then again, the direction is our angle. And we can find the angle theta using our tangent. So inverse tangent of y over x. So in this case, y is 200, x is 100. Okay, so when you type this in your calculator, make sure you're in degree mode because we're looking at degree angles. So when I type that into my calculator, I get 63.4 degrees. Now let's think about what that means. This is telling me the measure of this angle right here. Okay, it's telling you that this angle, theta, is 63.4 degrees. Now, that measurement doesn't really make sense yet because we have to apply our directions. So remember, this way was east, this way was south. So we're going to label this angle like we would with our cardinal directions. Okay. When I look at my picture, if this is where the 63.4 is, I went 63.4 degrees south of east. I'm a little bit below east, because we're actually using directions to solve this problem. Okay, if you wanted to think of it like our regular coordinate plane, drawing in your axes, this is kind of like the last one we did in the previous example. It's before 360. So 360 minus 63.4 would give us the 296.6 degree angle. Since there's no cardinal directions here, this is matching up to our regular system. Okay, I'm fine with either answer in this case, probably the direction one since we gave directions in the problem. Okay. All right, a couple more here. So here we're giving you some information about the components of the vector, so the horizontal and vertical distance. We're going to write the vector and then find the direction and the magnitude. So this is my horizontal. Okay, that's like our x. Vertical is like our y. So if I'm going to start by drawing this guy before I do anything else. So horizontally I went 3 units. Vertically I went 4 units north. Right, east and north, so we're using those directions. So it ends about here. Okay, we can assume we're starting at the origin. Here's east, and here's north. If I'm going to write this as a vector, remember I use the pointy brackets. So we're just filling in. Our x distance was 3, vertical distance, y distance was 4. That's my vector notation. The magnitude, I'll calculate in this bigger box here. The magnitude I can find, I'll just write m here for now, by doing our Pythagorean theorem, so square root of 3 squared plus 4 squared. Type that all in my calculator, I get 5. The direction I can find by doing inverse tangent of 4 over 3. Type that in my calculator, I get 53.1 degrees, and then I look at my picture, I'm going north of east. Okay, so you can fill these in here. 53.1 degrees north of east, not the biggest boxes. Alright, looking at the next one, I'm giving you some different information to start. So I'm giving you the actual magnitude and then angle here. Since there's no cardinal directions, we're going to draw this just like the angle from our regular coordinate plane. So 113 degrees is in quadrant 2. Now we don't need to be perfect here, just something in quadrant 2. Right, and this is where that 113 degrees is from. Okay, our regular coordinate graphing system. Now I know the 13 units is the magnitude, meaning it's the distance of this arrow. It's how long that arrow is. So I'm going to put my 13 on it. I'm looking to work backwards to the x and the y. So this is going back to SOHCAHTOA problems. Here's y, and here's x. Okay. Now before I can do that, I need to figure out what my reference angle is. Remember, we have 180 over here. If I want to figure out that little angle, I can do 180 minus 113. So I know this little angle is 67 degrees. Okay, now what I want you to do is figure out x and y. You're going to need your calculator because they're not the nicest numbers, and see if you can use SOHCAHTOA. So you have to kind of go back to thinking about SOHCAHTOA to calculate x and y here. So I'm going to pause the video, try this problem, see if you can finish that one up, and then see if you can do the one at the bottom. And then when you press play, I will have the answers up here for you. Alright, so here is the rest of my work for that problem. The only thing I want to point out here is your x coordinate. When you type in your calculator, it'll give you a positive number, but we know it should be negative because we're in quadrant 2, so just be careful there. So you can pause and kind of look at this work a little bit further. And then the other problem I wanted you to try was down here, another airplane problem. Again, you can pause the video so you can look at the work closely. I'm fine if you give your answer in your cardinal direction. Sometimes that's easier because you don't really have to change the number. You just have to write the correct version of the directions. But if you wanted to write it in terms of like the regular, circle type direction or angles, here's my work for doing that as well. Okay.